Good morning, sir. My name is Pratibha. I have chosen the seminar topic as Verification by Model Checking under the guidance of Dr. Srinath sir, Department of CSE, Bengaluru. This is the agenda which I am going to cover. First is motivation for verification, model checking. In that we will study the difference between the model checking and alloy, temporal logic, linear time temporal logic. In that we have syntax, connectives, examples, semantics, and important equivalences between LTL formulas, adequate set of connectives for LTL. Moving towards modification for verification. First, verifying the correctness of a computer system or programs. Next is what is advantage. Advantage is that to verify the correctness of a computer system, whether they are hardware, software, or a combination. Okay, this is used in case of safety critical system, but applies to those that are commercially critical, such as mass produced chips, mission critical systems, etc. Moving towards formal verification methods are most usually used in industries, and they are growing demand for professionals for use them. Next, we see what is formal verification techniques. Formal verification techniques comprise of three techniques. Those are a framework, a specification language, a verification method. A framework for modeling system typically is a description language of some sort. Then a specification language is used for describing the properties to be verified. Third is the verification method to establish whether the description of a system satisfies the specification. Moving towards the approaches of verification, those are classified into 5 types. Those are proof-based versus model-based, degree of automation, full versus property verification, intended domain of application, pre versus post-development. The first is proof-based versus model-based. In proof-based approach, the system describes a set of formula such as gamma, and the specification is another formula phi. The verification method consists of trying to find a proof such that the gamma is sequent to phi. This validity holds. Next, in model-based approach, what happens is the system is represented by a model M of an appropriate logic. The specification is again represented by a formula phi, and the verification method consists of computing whether a model M satisfies the phi, which is written as M is subtails to phi. Okay, this computation is usually automatic for finite models. Next, moving towards degree of automation. Under degree of automation, approaches differ on how automatic the method is. The extremes are fully automatic and fully manual. Many of the computer assisted techniques are somewhere in the middle. Next is full versus property verification. Under this, the specification may describe a single property of a system, or it may describe its full behavior. Then intended domain of application speaks about the hardware or the software, whether it is sequential or concurrent, reactive or terminating. We say a system is reactive, which reacts to its environment and is not meant to terminate. Example: operating system, embedded systems, and computer hardware. Pre versus post development. Verification is of a greater advantage if introduced early in the system development, because errors caught earlier in the production cycle are less costly to rectify. It is mostly used in terms of Pentium chip with the FDIV error. Next, moving towards model checking. First, what is model checking? Model checking is an automatic model-based property verification approach. It is intended to be used for concurrent reactive systems and originated as a post-development methodology. Next, model checking starts with a model described by the user and discovers whether the hypotheses assisted by the user are valid on the model. Then model checking is a process of computing an answer to the questions of whether the model M, which is denoted as this way, M, S, phi holds, where phi is a formula, M is an appropriate model of the system under consideration, S is a state of the that model, and is the underlying satisfaction relation. Now, moving towards what is the difference between model checking and alloy. As we have seen in the previous chapters and all, alloy is a system which is also automatic, model-based property verification approach. The next, alloy finds models which form counterexamples to assertions made by the user. Then the another difference between these two, that is the model checking and alloy, is model checking focuses explicitly on temporal properties and temporal evolution of the systems. Temporal logic. Model checking is based on temporal logic. Okay, this can be also called as a definition of a model checking. That is, the idea of a temporal logic is that a formula is not statistically to be true or false in a model, as it is in the proposition and predicate logic. That is, the model of temporal logic contains several states and formulas that can be true in some state and false in other state. Thus, the static notion of truth is replaced by dynamic one, in which the formulas may change their truth values as the system evolves from state to state. In model checking, the model M are transition systems and properties phi are formulas in temporal logic. Next, in order to move towards the linear time logics, think of time as a set of paths, where a path is a sequence of time instances, okay, which are used for studying in analog computers. Next, what is branching time logics is another one. It represents a time as a tree, where linear time represents time as a set of paths, branching time represents a set of time as a tree. Rooted at the present moment and branching out into the future. Branching time appears to make the non-deterministic nature of the future more explicit. Usually preferred for synchronous network. Next, another quality of time is whether we think of it as a being continuous or discrete. Whereas we can say LTL as continuous and other as discrete. Next, moving towards the linear time temporal logic. As we said, linear timing logic is been based wherein the time is thought of as a set of paths. Okay, where path is a sequence of time instances. Linear time logic, or shortly we call it as LTL, is a temporal logic with connectives that allows us to refer to the future. It models time as a sequence of states extending infinitely into the future. This sequence of state is sometimes called as a computation path or simply a path. That is, the future is not determined, so we consider several paths representing different possible futures, any one of which might be actual path that has been realized. Say, suppose we can even say that is a fixed set of items of atomic formula such as P1, P2, P3, P4 or Q, P, Q, R. We can take these as some of the atomic examples. Okay, like these items can be represented as printer Q4 is busy, processor 32 is suspended, etc. Then logic where time is linear is called a temporal time logic, shortly denoted as LTL. Then moving towards syntax of LTL, the definition goes in this way. That is, it is defined as phi has been defined to be tautology, contradiction, proposition P, negation of phi, phi and phi, phi and phi, phi or phi, phi implies phi, x of phi, then f of phi. These abbreviations have been defined in next slide, where P is this P is the propositional atom from some set of atoms. Okay, these are the connectives of LTL. Okay, what these are described, basically they are classified in these, that is X, F, G, U, R and W. X signifies the next state, F means some future state, G means all future states that are globally, U means until, R is the release and W is the weak until. These are some of the examples of LTL formulas. Okay, wherein in last slide we have seen the tautology and contradiction symbols, which are also an LTL formulas, as the all atoms from atoms, and negation of phi is a LTL formula if phi is 1, etc. Okay, these are some of the examples. If even we can ignore the braces also. this is the example, the past tree for the example, this one. F of P implies G of R, or negation of Q until P. This is the figure, diagrammatic figure for this, which means here for some future state, the P implies to a globally global state R with conjunction not of Q until P. This is okay. This was with respect to the parenthesis diagram. Next, this is the past tree of the same example without parenthesis, assuming binding properties of convention. What do you mean by binding properties convention is that the unary connectives such as negation and temporal connectives X, F and G bind most tightly. Next in order comes the until, R and W. Then comes the negation and then comes the conjunction and disjunction, and after that comes the imply symbol. Next is the okay. Well, some of the not well formed formulas are okay. Previously, these examples were the well formed formulas. They satisfy the conditions of the following are the not well formed formulas. That is, we can't write in this way. Until R, since U is binary and not unary. P globally Q, since G is unary, not binary. Then next goes the definition of some formula. In the how it is defined is, phi is any formula psi whose past tree is a subtree of a phi's past tree. The subformula of P and weak until of Q until R. Example is that P written as P Q R Q until R, and P weak until of Q until R. Moving towards the semantics of LTL, wherein the systems are been verified or modeled as transition systems. Okay, what do you mean by transition system? What definition of transition system is defined as? A transition system, say suppose a model M which is defined to be in this set of parentheses, that is S implies comma L, where S is a set of states with the transition relation implies, that is a binary relation on that state S, such that every state S that belongs to state has some S dash of has some state S dash that belongs to S, with S tends to S dash, and labeled function L which is defined to be S implies to P of atoms. The transition system models a system by means of states that are static structure and transitions that are dynamic structure. Transition systems are also simply called as models. So a model has a collection of states S. A relation implies saying how the system can move from one state to another, and associated with each state S, one has a set of atomic propositions, that is L of S, which are true at a particular state. Then power of atoms is written as in this way: P of atoms is the power set of atoms, a collection of atomic description. Okay, this is the one example of that. The power set of P comma Q is written as phi P Q P comma Q. Next, okay, we can think about L as that it's an assignment of truth values to all the propositional atoms. The difference is that we now have more than one state, so it depends on which state S the system is in. That is, L of F contains all the atoms which are true in state S. Okay, next, expressing all the information about a finite transition system M using a directed graph whose node contains all propositional atoms that are true in that state. For example, if we consider a system that has only three states, that is such as S0, S1 and S2, wherein if only possible transition between these states are S0 implies to S1 and S0 also implies to S2, S1 implies to S2 and S2 it implies to only S2. That is, this transition is going from S2 to S2. Which can be written in the label function such as L of S0 equals P comma Q, L of S1 equals Q comma R, L of S2 equals R. Okay, for every state S that belongs to some state S, there is at least one possible state S dash that belongs to S, such that S implies to S, means that no state of the system can deadlock. This is the concerned representation of the transition system M, which is represented as S implies L as a directed graph. Okay, now okay, if a system did deadlock, we could always add an extra state SD representing a deadlock together with a new transition S that implies to SD for where each S which was a deadlock in the old system, such as SD implies to SD. Okay, which is shown in next figure. In this figure, here in this figure there is no deadlock, since each state is making a transition to the other state. Okay, in this figure 5 there is a deadlock that is here in this right side of the figure. That is SD. We are presenting a new state SD here. Next, the definition goes: a path in a model M is defined to be S implies L is a infinite sequence of state S1, S2, S3 in some state S, such that for each I that is greater than or equal to 1, we define Si to be Si plus 1. We write it as S1 implies to S2, S2 implies to S3 and so on. Okay, considering the paths such as pi, in which S1 implies to S2, so on, it presents a possible future of our system. First, it is in the state S1, then it is in state S2 and so on. Then we write pi square for the suffix starting at Si. Then pi cube as S3 to S4 and so on. This is the figure for unwinding the system of the figure shown before. Okay, is an infinite tree of all computation paths beginning in a particular state. This is the diagrammatic view of this figure. Okay, what happens is all computation paths from a given state is unbindings the transition system to obtain an infinite computation tree. Okay, for example, if we unwind the state graph that is shown before for a designated starting state S0, then we get the infinite tree in this figure. The execution path of a model M are explicitly represented in the tree obtained by unwinding the model, which is defined in this way. Say suppose M is defined to be in the set of these parentheses, be a model, and pi as S1 to S2 to so on, be a path in M where pi satisfies an LTL formula is defined by the satisfying relation as follows, where pi talk and so on. These are the some of the relation, satisfying relation. Here, clause 1 and 2 reflects the fact that okay, from here, clause 1 and 2 represents the fact that tautology is always true and contradiction is always false. Clause 3 and 7 are similar to the corresponding above clauses in the propositional logic. Clause 8, which means this one, removes the first state from the path in order to create a path starting at the next state. Moving towards the next clauses, wherein from 11 to 13 deals with the binary temporal connectives, such as weak until. In the clause of 11 to 13, here we define that is the binary temporal connectives such as until, weak until, and release. Okay, with until, which is most encountered for one of these, the formula phi1 until phi2 holds on a path if it is in the case that phi1 holds continuously until phi2 holds. Okay, next, phi1 until phi2 actually demands that phi2 does hold in some future state. The other binary connectives such as weak until, and release, which is same as until, except that phi until weak until psi does not require that psi is eventually satisfied along the path in questions. Next, moving towards the important equivalences between LTL formulas, which is defined to be, suppose two LTL formulas phi and psi are semantically equivalent or simply equivalent, which is written as in this way, that is phi is semantically equivalent to psi. If all model M and all paths pi, which is defined in this way, M pi psi if pi entails to psi. The equivalences of the pi and psi means that pi and psi are semantically interchangeable. In proposition logic, we say that conjunction and disjunctions are duals of each other. Similarly, meaning that if you push a negation past a and symbol, it becomes a or, and vice versa, which is shown in this formula. Okay. Then similarly for which holds even for the some future state and some globally future states are duals of each other, and X is dual with itself, which is the equation of this. For some not of some globally future state phi, which is equivalent to future state of not of phi. Next, until and release are duals of each other, which is negation of phi until psi, which is logic equivalent to not of phi, release not of psi. Then moving towards adequate set of connectives for LTL, wherein small adequate sets of connectives also exist in LTL. Here is the summary of the situation. Here X is the next state is completely orthogonal to the other connectives. That is to say, its presence does not help in defining any of the other ones in terms of each other. That is, X cannot be derived from any combination of the others. Each of these sets, that is until X, this is one set, the other set release comma X, weak until of X is adequate. Okay, to see that we define in this way. Release and weak until may be defined from until by the duality as phi release psi is logically equivalent to negation of phi not of phi until not of psi. Next is until and weak until may be defined from R by the duality of phi until psi, which is logically equivalent to not of phi release not of psi, and similarly goes for release and until, which may be defined as which may be defined from weak until. That is phi until psi, which is defined to be psi not of phi release not of psi, followed by the equivalences. Thank you.